Electronegativity. Group 14 elements are slightly more electronegative than group 13 elements. Physical properties. Group 14 elements are solids. Carbon and silicon are non-metals, whereas germanium is a metalloid. Tin and lead are soft metals. Chemical properties, in that first we shall discuss about oxidation states. Group 14 elements have 4 valence electrons. We know that the general outer electronic configuration is Ns2, Np2. So they have 4 valence electrons. Therefore, the common oxidation states are +4 and +2. Carbon exhibits negative oxidation state. In addition to +4 and +2 oxidation state, carbon can exhibit negative oxidation state. The tendency to show +2 oxidation state increases down the group. It is due to inert pair effect. Tin forms compounds in both +2 and +4 oxidation state. For example, if we consider compounds of tin, that is SnCl2 stannous chloride. In stannous chloride, tin exhibits an oxidation state of +2. Tin forms stannic chloride SnCl4, in which the oxidation state of tin is +4. Thus, tin can form compounds in both +2 and +4 oxidation states. The maximum covalency of carbon is 4. It is because carbon does not contain any d orbitals. Whereas silicon can exhibit a maximum covalency of 6. It is due to the presence of d orbitals. For example, silicon can form SiF62-, in which the state of hybridization of silicon is sp3d2. Reactivity towards oxygen. Group 14 elements react with oxygen and form oxides. They form both monoxide and dioxide. Monoxide of the formula MO and dioxide of the formula MO2. Oxides in higher oxidation states are more acidic. Carbon dioxide, silicon dioxide and germanium dioxide are acidic in nature, whereas the oxides of tin and lead, that is SnO2 and PbO2, are amphoteric in nature. Carbon monoxide is a neutral oxide. Germanium oxide is acidic. The oxide of tin, that is SnO and PbO, are amphoteric in nature. Reactivity towards water. Carbon, silicon and germanium are not affected by water. Tin reacts with steam to give oxide of tin, that is SnO2, with the liberation of hydrogen gas. Reactivity towards halogens. Group 14 elements react with halogens and form 2 different halides of the formula MX2 and MX4. So they form both dihalides and tetrahalides. MX4 is covalent in nature. For example, carbon tetrachloride. In carbon tetrachloride, carbon is under sp3 hybridized state and the shape of carbon tetrachloride is tetrahedral. Stability of dihalides increases down the group. PbX2 is more stable than PbX4. Now consider silicon tetrachloride. It undergoes hydrolysis and forms SiOH4 times, which is silicic acid. Anomalous behavior of carbon. Carbon differs from the rest of the elements of group 14. It is due to its small size, higher electronegativity, higher ionization enthalpy and unavailability of d orbitals. Maximum covalency of carbon is 4. It is due to the absence of d orbitals. Carbon can form p-pi multiple bonds. For example, consider an alkene, that is ethene. In ethene, there is carbon-carbon double bond and the double bond is made up of 1 sigma bond and 1 pi bond. Now, how is the pi bond formed between the 2 carbon atoms? By the sideways overlap of the p orbitals of both the carbon atoms. So, carbon can form p-pi multiple bonds. Another property associated with carbon is catenation. We know that carbon can form bonds with other carbon atoms and can result in the formation of large molecules. So, this property is known as catenation. Allotropes of carbon. Diamond and graphite are the crystalline forms of carbon. Carbon also exists as fullerenes. Consider diamond. It has a crystalline lattice. In diamond, Each carbon is sp3 hybridized and each carbon is bonded to 4 other carbon atoms in a tetrahedral fashion. So diamond has a rigid 3-dimensional structure. It is very difficult to break the extended covalent bonding in diamond. So diamond is the hardest natural substance.